Hello all. In this lecture, we will see some introduction about database design, and also we will see informal guidelines to database design. So, in the 17th lecture, we have seen how to map entity relationship diagrams to relations. So, we have mapped those. In the database design, what we do is we'll first try to draw the entity relationship diagram. After from that entity relationship diagram, we try to map it into tables or relations. Now, next step is to check whether those relations or tables are good or bad. So we'll see what do you mean by this good table or good relation and bad relation in this lecture. So next step is to map those relations or to change those relations or tables into good tables or good relations, or we call it as normalization. So we'll be studying about normalization in the next few lectures. Okay. So we will see in this lecture, we will see what do you mean by this database design. Then we will see informal guidelines. We have mainly 4 informal guidelines to database design. We will see all those 4 guidelines. So we'll see what is a relational database design. So it is the grouping of attributes to form good relation schemes. Good relation schemes. So we have to group attributes such that we have good relations or good tables. So what do you mean by this good relation schemes? So we'll be seeing what this goodness of relation schemes in this chapter. Okay. So goodness, we have 2 levels of relation schemas. So we have already seen this. The one is a logical user view, or we call it as a conceptual level schema. Conceptual level schema. And the second one is a storage or base relation, or we call it as physical storage level schema. So we have mainly 2 levels of schema. One is a logical or the conceptual schema. So we will learn about this physical storage later. Okay, actually it was in the 3rd module, but now we have started this 4th module. So later we will be seeing about this conceptual, the storage level schema, that is a physical level schema. So now we will be seeing about the conceptual level or the logical level or the user level schema. So how to make those relation schemas a better one. So design is concerned mainly with this base relations. Okay. So what are the criteria for good base relation? So we'll be seeing what are the criteria to make it into a good relation. So we mainly in database design, we have 2 types of methodology. We can design in 2 ways. One is bottom-up design methodology, or we call it as synthesis also. It is designed by synthesis. Bottom-up design methodology, or it is known as design by synthesis. What we do is in bottom-up design, we start with relationships among individual attributes. So we will start from relations with among individual attributes. So we have a set of relationships. We know a set of relationships between some attributes, and we start from that and we try to develop a good relation design. Then second method is top down design methodology. It is also called design by analysis. So it is also known as design by analysis. Here what we do is starts with a number of groupings of attributes into relations that exist together naturally. So what we do is we start with some groupings of attributes. That is, we have some basic relations or basic tables are there. We start from this thing, then we will try to design it properly. Okay. So here what we do is the relations are analyzed individually or collectively, and then we will again decompose so that some desirable properties are made. So this is where we can do this design. So we will be mainly focusing on this top-down design methodology. Okay, top-down design methodology. So we have a set of relations. We have already formed ER diagrams, and from that ER diagrams we have mapped it into some tables. Now what we have to do is we have to check whether it is good or bad. So those relationships are good or bad. So what we have to do in relational database design is to ultimately it produces a set of relations. It will be a set of relations which will preserve all the information. So information should be preserved. That is, if we have a set of attributes at the initial stage or some relationships between these attributes in the initial stage, all those attributes and those relationships should be preserved after completing this database design. So that is known as information preservation. Then the second property that should be satisfied is we should minimize this redundancy. That is, we should not store redundant information, or we should not repeatedly store some information. For example, if I want to store a student's phone number, it should be stored only once in any of the tables. It should not be repeatedly stored. For example, Atul's phone number is this 10-digit number. It should be stored only once in the table. We should minimize that redundancy. It should not be stored 100 times. The same thing should not be stored 100 times. So we have to minimize this redundancy. So good database design means it should have this information preservation, that is, whatever attributes and whatever relationships between those attributes existed should be there in the final design also. And also we should minimize this redundancy. So redundancy is a big problem. We will see what are the problems associated with this redundancy in this lecture itself. Okay. Now we will see some of the informal design guidelines. So these are all informal guidelines. We will see about formal guidelines in the next lecture. In this lecture, we will simply see about informal design guidelines for relational database. So first informal guideline is make sure that the semantics of the attributes is clear in the schema. So we should make sure that the semantics or the meaning of the attributes is clear in the schema. In the schema means in the tables. Second one is we have to reduce the redundant information in tuples. So whatever tuples we have, there should not be redundant information. That is, we should not repeatedly store some information in the tables. Reduce the null values in tuples. We should reduce the null values. That is, null values we have already seen. There are three cases where we insert null values in the tables. So we will see all those three cases in this lecture also. So we should reduce the null values in tuples, and also we should disallow the possibility of generating spurious tuples. So we will see what is the spurious tuples also in this lecture. So these are the four informal guidelines for relational databases. Okay, we will see one by one. First one is semantics of the relation attributes. So guideline 1, informally, each tuple means each row in a relation, each row in a table should represent one entity or relationship instance. So this actually guideline 1 applies to individual relations and their attributes. So whenever there is a row in a table, that one row should represent only one thing. We should not store multiple things in a table. That's the main thing. So if we have a row or if we have a tuple in a table, we should store only a single kind of thing in a single row. We should not store multiple students data. If I am storing some students table data in a table, I should have, if first row is designated for is for Atul's data, then it should contain only Atul's data. I should not store Arun's data in first row. Okay, so that is each tuple or each row in a relation should represent one entity or one relationship instance. Okay. So attributes of different entities, that is employee, department, project, should not be mixed in the same relation. So we should not mix all these attributes in a single relation. So if it is employee attribute, it should be in a separate table. If it is department attribute, it should be in a second different table. If it's project attribute, that should be in different relation. Okay. So it should not be mixed. All these attributes should not be mixed in a single table. So, for in order to show the relationship between this employee department or employee project, we should use foreign keys. So we have already seen what is a foreign key. So we should use foreign keys should be used to refer to other entities. So if we want to refer something, if we want to show some relationship between employee and department, we should use foreign keys instead of storing everything in a single table. So entity and relationship attributes should be kept apart as much as possible. So all these entity and relationship attributes, if they are different, it should be kept apart as much as possible. If we do not keep this, there will be some problems. We will see all those problems. So this is an example of a good relation or good design, because in this table we have employee. So this is a relation employee. If we see the attributes, here we have e name, SSN, B date and address, and additionally we have D number, but this is a foreign key. This is used to refer this department table. Here we have D name, D number, D manager, SSN. Okay. Here this is department locations. This contains only D number and D location. D number will be used to refer this department. Then project also, we have only project name, project number, project location and D number. So this D number is the foreign key. This is used to refer this thing. Here works on, we have only SSN and P number and hours. The SSN is the foreign key to refer this employee table. Okay. So we are not mixing up the employee and department. We simply use a single attribute or set of attributes as foreign key to refer different relations. So we will. So this is a good design. So this is following guideline 1, because each entity or each relation. So this is a guideline. Informally, each tuple in a relation should represent one entity. So if we take any rows in any of these relations, it will represent only a single thing. It won't it won't it won't store multiple data, multiple things or multiple relations in a single row. So this is an example. So if you see the first row, Smith John. So this is the data about Smith John itself. Or if you take this department, we can see that this is research department data, or this is about department 1 data. So if you see works on also, we can see that one row, this represents about this 1 2 3 4 5 6 working on project number 1, and this row represents this same employee working on project number 2. So each row represents a single thing. Now we will see a violation of this guideline 1. So this is a good relation. This follows guideline 1. So this is a violation of guideline 1. So if we have some relation like M department, so this is a violation. So in this we are storing employee attributes, and also we are storing department attributes also. So this is actually a violation of guideline 1. This is violating guideline 1 because we are storing multiple information. So if we have, so if we, so, okay. So if we have this, if we see this table, what happens is we are storing the department details also in each row. So if there are 100 employees, working in a particular department, for example, computer science department, we have 100 employees. So what happens is the 100 times we will be repeating this department name and department manager SSN. So in this table itself, if we have 100 employees working in a particular department, we will be repeating that, we will be redundantly storing that information. That department name is CSC and department manager is some person, Praveen. That person is the department manager. So that information will be redundantly stored in this relation or in this table. So that is a problem. So this is a violation of guideline 1 because we are mixing up of these attributes. We will not be storing a single, in a single tuple, we will be storing multiple data. We will be storing some other relation data also. Okay. So this is another example of violation of this guideline 1. Here we have SSN, P number, hours. Then we are mixing employee name here. Then we are mixing P name here, P location here. This is also a violation of guideline 1 because all these are attributes of different relations. So these attributes should be stored in different tables. Otherwise, there will be redundant information in this table. So this is a violation of guideline 1. So we will see what is the problem with this redundant information in tuples and update anomaly. So we have already mentioned that there will be redundant information in this table. So what is the problem with redundant information in tuples? And what are the anomalies that will happen? We call it as update anomalies that will happen when we store redundant information in a relation. So here redundant information means that information is stored redundantly or repeatedly we'll be storing some information. So what happens is, it's one thing is there is wastage of storage. So storage will be wasted because in the previous example, if you see, if there are 100 employees working in a particular department, we are unnecessarily storing that department name and department manager in this employee table itself. In this table itself, we will be unnecessarily repeatedly storing that thing. Okay, so it is wastage of storage, and it also causes problems with update anomalies. It is not only storage problem, we have some update anomalies. Update anomalies, we have mainly three types of anomalies. One is insertion anomaly, second is deletion anomaly, and third is modification anomaly. So all these three anomalies together is known as update anomalies. Okay, all these anomalies together are known as update anomalies. So we have insertion anomaly. Insertion anomaly means if we try to insert something into a redundant information table, then there will be some problem. When we try to delete also, there will be some problem. When we try to modify or update some information also, there are some problems associated with this thing. So we will see the different update anomalies. So if we show redundant information, these update anomalies can occur. So we will see an example for this insertion anomaly. So this we have already seen, there is redundant information in this table. So if we take the extension or the state of at a particular instance, we can see this is the table, M department with something like this. So if we see this, there are 4 employees working in research department. So this is repeated. Research, here again research and the manager assistant. Here again research and manager assistant is repeated. Similarly for administration, we have 3 employees. So this information is repeated. We are repeating this administration, and the D manager assistant is repeated again in 3 rows. So this is actually the violation of guideline 1, because we are store redundant information, there is redundancy. So what is a redundancy? What if we try to insert something? So if we want to insert into this table, there will be some anomaly. So if you want to insert a new employee into this table, so insertion anomaly means when we try to insert. So when we try to insert a new table into this employee department, what we have to do is we have to enter the value of the department number and also this department name and department manager SSN. So if the employee does not work for any department, when an employee joins a company, he may not be assigned any department. So if he is not assigned any department, then that employee cannot be inserted into this table, because this department number, department name, department manager's SSN should be entered. Okay, and also if he is assigned a department, also if for example if he is assigned a department number as 5, then when we insert a new employee into that table, what happens is we have to enter the D name and the D manager SSN correctly. If we incorrectly enter the department name and D manager SSN value, then there will be problem also. So this is actually, these 2 rows are redundant information. If a new employee is inserted, he should be given a department. Then only we can be that data can be entered into this table. And another problem is when we try to enter a new person into this table, he should when we enter that data, we should make sure that the D name and D manager SSN is entered correctly. Okay. So that is one kind of insertion anomaly. Another kind of insertion anomaly can occur in this table. Since we are storing everything in a single table, now we have formed a new department. For example, we are forming a new department called mechatronics. So we cannot store the data about this mechatronics department in this table unless we have an employee working in that department. So there should be at least one employee that will be working in that department. Then only we can enter a new department into this table. For example, if you want to enter a new department with a department number 7 into this table, it is not possible because we have to enter SSN value, because SSN is the primary key of this table. Since SSN is a primary key, we need to assign at least a new employee, at least one employee to that new department. Okay, so that is insertion anomaly. So when we try to insert something into this table, this anomaly can occur. Okay, so if we have divided into this kind of thing, so if we have divided this M department into two tables like employee and department like this, and only this D number will be used to refer this primary key. This is a foreign key and this will be used to refer this primary key of this D number, then there won't be any problem. Any insertion anomaly won't be there. So if we want to try, if we want to insert a new employee, we can simply insert a new employee into this table. Or if we want to insert a new department, it is possible we can simply insert into this table without without a new without any employees in that department. Okay. So insertion anomaly won't occur if we are splitting into this thing. So another example we will see about insertion anomaly, if we have some table like M project and here M star employee number and the project number, this combination is the primary key of this table, and these are the other attributes E name, P name and number of hours. So the insertion anomaly occurs. We cannot insert a project unless an employee is assigned to it. So if you have a new project into this company, it cannot be inserted into this table because this combination is the primary key. So if you want to enter a project, then an employee should also be entered. Then only we can enter that thing. Okay. Conversely, if we cannot insert an employee, we cannot insert an employee into this table unless he or she is assigned a new project. Okay, because this is the combination. This combination is the key of this table. So this is known as insertion anomaly. So we cannot insert a project unless an employee is assigned to it, and vice versa. We cannot insert an employee unless he or she is assigned a project also. Okay. Then the second type of anomaly is a delete anomaly. So we will take the same example M department, and we have seen this these two columns are redundant information. So deletion anomaly. So what happens is if we want to delete Bo James E. So we have Bo James E. So if we see this, he is in department number 1, which is the headquarters department. Okay, so we want to delete Boj because he has left the company, and we want to delete this Bo James from this table. So what happens is this department will also get deleted because he is the sole employee in that department. No other person is working in department number 1. So if there is an employee who is a sole person employed in a particular department, and if you try to delete that particular person, this deletion anomaly occurs. This department will also get deleted. So that information will also be lost because of this. We call it as delete anomaly. So the department headquarters itself gets deleted. So this department itself gets deleted. So we just want to delete the employee because he has left this company. But what happens is department number 1 itself gets deleted. So we will see another example for this delete anomaly example. So we have this table. We will take the same example: emp number, project number, e name, p name, and number of hours. So delete anomaly occurs in this table also. So when a project is deleted, so when we try to delete a project, it will result in deleting all the employees who are working on that project, because this is combination is the primary key. So when we delete a particular project, what happens is all the employees working in that project will also get deleted from this table. Alternatively, if an employee is the sole employee on a project, if a particular employee is working on a single project, and then in that project no other employee is working, so what happens is deleting that employee would result in deleting the corresponding project also. So if that employee is a sole person working in that project, and if we delete that employee, that project will also get deleted. So this is known as delete anomaly. So this should not happen. Okay. Then we will see a modification anomaly. We will take the same table. What happens when we try to modify this table? So if we want to modify the manager of a department, so actually we want to modify this department manager. We have assigned a new person as manager of this department. So what happened? We have to modify each and every row. So if there are 100 employees working in this research department, we have to modify this 100 rows. We have to change the department manager SSN of those 100 rows. So that is known as modification anomaly. So if you want to modify the manager of a department, we need to update in all the rows or all the tuples. All the tuples should be modified. So you'll see another example. We have already seen this example: M project, employee number, project number, e name, p name, number of hours. So in this modification anomaly, so if you want to change the name of project number 1, P1, from billing to customer accounting, it may cause this update to be made for 100 employees working on project 1. So if that 100 employees is working on this P1, and if we try to change this project name from billing to customer accounting, if there are 100 employees working on that project, then we need to change the 100 rows, or the 100 tuples need to be updated. So we will see guideline 2. So design the base relation schemas so that no insertion, deletion, or modification anomalies are present in the relation. So this is guideline 2. So we have seen updation anomalies. So we should design tables such that this insertion, deletion, or modification anomaly does not occur. So this is guideline 2. This is just informal guideline. Okay. Then next you will see null values in tuples and guideline 3. So guideline 3, relations should be designed such that their tuples will have as few null values as possible. So when we have many null values in a table, that means there is some problem. So we should reduce the number of null values in rows. Okay. So attributes that are null frequently could be placed in separate relations with the primary key. So if there are many null values in a particular table, what we have to do is we have to split into two tables. We have to take those null valued rows and place it in another row with the primary key. So why these nulls occur in a relation? We have already seen these reasons in two other lectures also. So one thing is attribute not applicable or valid. So attribute may not be applicable or valid. For example, we have already seen which previous degrees of a person, previous degrees. Maybe he may not have any degrees. Then we should enter it as null. Then attribute value unknown, for example, date of birth of a phone number of a person, or date of birth of a person, that exists but it is unknown. It may exist but it is unknown. Okay, phone number may exist but it may not be it may not be known. So it is we will be entering null in the table. Then another condition is value known to exist but unavailable. So value is there, but it is unavailable at this situation. So all these conditions we call it as we will enter it as null values. So all these conditions this can occur. So what we do is in guideline 3 it is specified that there should be few null values. In order to reduce that null values, what we have to do is whichever column has null values, we separate that column into another relation, and in that relation the primary key of this relation will also be formed. Okay, so that is a thing we have to do. Okay, so when we want to reduce the number of null values, what we have to do is we have to separate those rows into a new relation. Okay, if for example department name is having so many null values, or date of birth is having so many null values, we take that date of birth into a separate table, and in that table include the primary key of this table also. So we can reduce the number of null values. Don't worry about this informal guideline. Automatically all these null values will be eliminated when we learn the formal way to design this table. So only thing we have to notice, we have to design such that there are few null values in the table. Then fourth is generation of spurious tuples. So spurious tuples should be avoided at any cost. So bad designs for relation database may result in erroneous results for certain join operations. We will see what is the spurious tuples and how the spurious tuples are generated. So we'll see that there is lossless join property is used to guarantee meaningful results for join operations. So when we design, it should satisfy this lossless join property. We will see what is this lossless join property later. So guideline 4 is the relations should be designed to satisfy the lossless join condition. So when we design these relations, it should satisfy this lossless join condition. Lossless join condition means no spurious tuple should be generated by doing a natural join on any relations. So we'll see what is this guideline for. Don't worry about this thing now. So it means that we should all the relations should satisfy this lossless join property. Lossless join property should be satisfied. When this lossless join property is satisfied, spurious tuples won't be generated. So we will see what is this lossless join and what is this spurious tuple. So we will see an example. So this is a table M project. These are the attributes in it: SSN, P number, hours, E name, P name, P location. And these are the functional dependency. We will see a functional dependency later. So if we are trying to split into two relations, so when we decompose, so we are already mentioned that in top-down design, what we do is when there is a table like this, we find that this table is not good. We try to make it into a good relation. What we do is we try to split into two, or we try to decompose that table. So if we decompose this table, we can get into like this: M locations. So E name and P location in a single table, and this combination will be the primary key of the table. And we have another relation with M project 1 with SSN, P number, hours, P name, and P location. So we have avoided that E name in this table and we have made it into another table. So this is a bad relation. Okay, these two relations. So this relation is split into two other relations. So this is a bad relation. Actually, this is a bad relation. And if we store the data, if we see the state of these M locations and M project 1, it will be like this: M locations. So Smith John is his project, he is working on two different projects. That is why one project is located in Bellare and second is located in Sugarland. Similarly, for other persons, so Wong, Franklin, one is at Sugarland and the other one is in Hausen. And another project is it is located in Stafford. Okay, so this is M locations. So this is different employees and they are different project locations. And we have another table. So we have split into M project 1. In here we have this SSN value, P number, hours, and P name and P location. Okay, this is So we have split into two tables. So this was the actual table, and we tried to decompose to make it into a good relation, and we have made these two tables. Now we have already learned in SQL that we will be joining these tables, and also in relational algebra also we will have seen that we will be joining these two tables. We have already seen natural tuple and spurious tuples when we learned relational algebra. You can refer the previous lectures. In that we have already mentioned about the spurious tuples. So how the spurious tuple occurs in this relation. So if we want to retrieve some information from this, for example, if I want to retrieve the SSN value of Smith John B, if I want to retrieve the SSN value of Smith John B, it is not present in this table, and Smith John B name is here. But if I want to retrieve his SSN value, then I have to join these two tables. I have to join these two tables together. Join means this table will be added with this table. Okay, so those two tables will be joined based on some attribute. So we'll be using some attribute to join these two tables. Here the join attribute is p location, natural join. We have already said natural join means the attribute name will be same. So p location, based on p location we will be joining these two tables. So when we try to join this natural join, the resultant table will be like this. So this is a natural join of M project 1 and M location. So when we perform natural join on these two tables, just for the employee this 1, 2, 3, 4, 5, 6, 9, we can simply check 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have simply joined you based on P location. Natural join means we will be joining based on the same attribute name. So we'll be joining based on P location, and the resultant table will be like this. Now there are some spurious tuples. If I try to find out the the name of the attribute, or if I want to find out the employee name corresponding to this 1, 2, 3, 4, 5, 6, 7, 8, 9, what happens is I will get another two attributes, that is Smith John B is also having SSN this same value, and English Joyce is also having the same attribute, and here so two employees are having the same SSN in this table. So this is actually the natural join. So all these starred rows or starred tuples are spurious tuples. All these are spurious tuples in the tables. These are all spurious. Star are all spurious tuples, because this is giving some wrong information. This is giving some wrong information. So if I try to find out the employee name corresponding to this SSN, I will get Smith John, I will get English Joyce, maybe sometimes I will get Wong Franklin also. So this is generating some spurious tuples or unwanted or unnecessary or erroneous tuples. Okay, all these are spurious tuples. Okay. So the problem occurred when we tried to split into these two relations. So these, if we try to split like this, there is a problem. Okay. So generation of spurious tuples occur because we have this lossless join property is is not satisfied. Lossless join property means when we try to split into these two tables, and again when we try to join these two tables, there should not be any spurious tuples or additional tuples or additional rows should not be there in these tables. If there are spurious tuples in these tables, that means this is a bad relation. We have many spurious tuples. So lossless join property is not satisfied. Lossless join property means when we try to join two tables, spurious tuples should not be there. Okay. So when we perform natural join on mproj and mlocation 1, there are many spurious tuples that are generated. So that means this is a bad relation. So there are two important properties of decomposition. One is non-additive or losslessness of the corresponding join. So when we perform join operation, there should not be any spurious tuples that should be generated, and also the preservation, all the functional dependencies should be preserved when we decompose into two or more relations. Note that property A is extremely important and cannot be satisfied. So this non-additive join property should be satisfied. Where there should not be any that lossless join property should be satisfied at any cost. It cannot be sacrificed. And in the case of dependency preservation property is less stringent. It may be sacrificed in certain cases. We'll see what is functional dependency at all in later lessons. So then you will understand what is this functional dependency preservation and all. So this is a summary. We have seen different anomalies, wastage of storage spaces due to nulls, and generation of valid and spurious data during joins on base relations. This is a reference, and thank you.